So we thank Konstantinos, and we'll now hear from Mr. Dieter Rohdenburg, Managing Director of Intership Navigation, who will talk about accelerating decarbonization efforts through onboard carbon capture systems. Please welcome Dieter.
Thank you, Anna. Good afternoon, everybody. I won't be using this. Yeah. And let me first of all thank the organizers, Adonis and Stella, for organizing this event. I think it's been a fantastic conference so far, and more to come, of course. And congratulations on your logo as well. I like it. I think it's clear, clean, and I like particularly the blue dot there. So very good. Well, I guess I'm picking up from where Konstantinos just left it off, talking about carbon capture system. He was just briefly referring to this as one of the options, but I think it is actually potentially a very important option going forward to help us decarbonize the industry. Well, we talked already this morning about the other necessary steps that we all need to take to decarbonize the shipping industry. First and foremost, and short term, the increase of efficiency. We need to review our voyage planning. We need to review the vessel utilization, an important subject actually. I don't know if how many of you are involved in the operation of bulkers and tankers also, but bulkers, many of the bulk carriers, they don't go with full load. They load only part cargoes. We have an issue with voyage planning, all of us. We could potentially be saving a lot of fuel by not speeding up to get to the port of discharge and then wait there for days for berthing. So these are things which we need to address as an industry. And I think this is what we will see over the next few years accelerating. Technical efficiencies, there are new technical solutions now for retrofits. You will be aware of some of them, or maybe all of them, PCBF, coatings, anti-resistance, low-resistance coatings. We just talked about the wind propulsion. By the way, I don't know if Kim is still here. The last pictures, they looked as if you only carry wind turbines and no cargo anymore. I hope that's not the case. But very interesting as well. But the challenge is it's only 20, maybe 30% of saving there. So that's not going to get us to the finishing line that we all need to see by 2050. We just talked about the low carbon fuels as well. There's many of them. I forgot on the list here all the obvious, which is biofuels. And then, of course, methanol, ammonia as the most significant ones going forward. We didn't talk about nuclear fuel. It is an option. I think many of us will have our concerns with it, but there are discussions, molten salt reactors, for example, as potential, just extremely expensive at the moment. And finally, and that's what I will talk to you about, carbon capture. We are about to start a pilot project with a company that was actually listed on the list just now, that's shown by a previous speaker, which for a specific vessel and a specific trade, and this is what I want to talk to you about. The obvious benefits for carbon capture is that it will reduce the demand for low or zero carbon fuels. So we are not competing with the other, when you install this, you're not competing anymore for the other fuels, methanol and so on. It also reduces or eliminates the competition for sustainable biomass. Biofuels, even though they may be very interesting because they are easy to use and most ships are ready to use them, of course they are competing for land that could be used for production of food for human consumption. And there is a lot of land-based experience already. Carbon capture has been around for some time, both in the industry and also in the wider let me say, attempts to decrease the carbon in the air. There are challenges, there are obvious challenges to using carbon capture system. One of which I will talk about is weight issues. Keep in mind, every ton of fuel that you burn creates 3 tons of CO2. So you need to store that somewhere until you can give it a shot. And there are, as the previous speaker said as well, there are some systems in the market, but very few have actually been tested and taken through pilot phases. I don't want to go into detail because I can't. I'm not a chemist and I couldn't even explain this to you. But the process that I will be talking to you about is what is called adsorption. It is the process where a solid, which I explain, will be absorbing the CO2. As I said, this is a pilot project which we're about to start. The ingredients, the participants in this is first and foremost the equipment supplied by Seabound. And the Seabound system works in such a way that it uses quicklime, which is calcium oxide, which by default, by design, absorbs the CO2 and turns then into limestone. So quicklime is actually a product that is not found as quicklime. It is actually limestone, which through heating is then separated into CaO and CO2. And later, when you just have the quicklime, the quicklime gets hydrated, so then it doesn't absorb the CO2 automatically. But when it dries up, it automatically absorbs the CO2 again. Now we show you how it works. We will be doing this on one of the Hartmann ships. Hartmann has a cement carrier called UBC Cork. It's a relatively small vessel, 8,000 metric tons deadweight, trading along the Norwegian coast. And I'll explain also why we chose this vessel. The third partner in this is the charterer, the end user of the cement, which we carry. And that's actually the reason why we use this ship, a potential user of the limestone that we will be producing by having the quicklime absorbing the CO2. Limestone is an ingredient for cement production, and so that's how we thought, wow, this could be a win-win situation. So this is a schematic drawing of what's happening. Here's the engine. The exhaust passes through the carbonator, and the calcium oxide absorbs the CO2, turns it into calcium, what's it called? Calcium carbonate. And this is what happens on board of the ship. Then you pass this on shore, and through this operation here, which is again heating up the calcium carbonate, it separates again the calcium into the calcium carbonate into calcium oxide and CO2, and you end up with pure CO2, which you can then either sequestrate and put it in the ground, or you can reuse it and use it in industrial production, or alternatively use it to produce fuel again. So it becomes a circular movement. I think the previous speaker was also talking about this already. So this is the vessel. It's a cement carrier. Those of you who don't know cement carriers is essentially tankers. They carry powdered cement, dry. That makes it different from a normal tanker. But they essentially work like a tanker with pipes. You blow the cement out with big compressors that you see on deck there, which are actually blowing the cement up to 2 kilometers far away on shore. And this is the trading area. Just a brief, a small picture of the Norwegian coastline. The important part here is that the voyages are very short. So you have typically, within a week, you can have 5 discharge ports. So very short voyages, which certainly for the pilot phase is important, but it also is an issue for the business case of using CCS. As I mentioned, for every ton of fuel you burn, you have to store at least the 3 tons of CO2 that you create on board of the vessel. So if you have a very substantial fuel consumption, you end up carrying only CO2 at the end. The system that we will be using is a modular containerized system. Essentially, it contains 20 tons of pebbles of the quicklime, and the CO2 from the exhaust will pass through the container. It will go through the pebbles. The pebbles, at the same time that they will dry up, so they dehydrate, they will absorb the CO2, and essentially the CO2 replaces roughly the water that is within the pebbles, and so you are capturing the CO2 in these containers. The containers can be, this is a scalable system. They can be stacked to any heights and tiers, so you can use this on a relatively large scale. We will be starting only with 3 containers initially, and one of the reasons why we picked this vessel for this, besides the point of the short voyages and the end user of the cement, was the fact that she actually has container storage capacity behind the superstructure. What you see here in blue, and after the superstructure, this is the stack of containers that we will be using. And you see it's also easy to pass the exhaust fumes from the exhaust pipe through the container. In front of the superstructure is some supporting equipment. You need some booster pumps, booster blowers to counteract the back pressure that is created by passing the exhaust through the containers. So that's some additional equipment that is needed. Yeah, I explained the setup. So what's the business case? Well, I said, actually the reason why I started this was, you get limestone. Limestone is used in cement production. This must be a win-win situation. So that's how we started discussing that. But of course, there's more to it. The first, probably, it is a monetary benefit, but it is very much also a reputational benefit for the cement producers. They want to be seen to be doing something to decarbonize their own industry, which also means that they really have to look at the Scope 3 emissions, so their suppliers' emissions as well. So they are looking now at how they can bring the fleet that they are using to decarbonize within the next few years, and that's one of the means for it. You're saving in the CO2 emissions trading schemes. You don't have to buy EUAs anymore. Norway is part of the EUA system, the ETS system. Cost at the moment are, of course, less than $100, but people expect that when shipping is fully part of it, then it will certainly go up, maybe $150, $200. This will be roughly the cost also of the system, the operating cost of this system. Initially, it's higher. I see my time is up, so I have to be a little bit faster now. Short voyages I mentioned already, by the way, this also reduces the sulfur content, so it is actually acting as a scrubber as well. I won't go through this. I just wanted to point out here, again, one of the big challenges is the weight. You have to have, for every ton of CO2 that we capture, we need about 1.5 tons of pebbles. So the pebbles, when they absorb the CO2, they enrich. So I mentioned that they will essentially replace the water that is in there, but every container can take up to 10 tons of CO2. The weight of a container is 28 tons. So it's 10 tons of CO2 means 3 tons of fuel. So you need a lot of containers. It makes sense when you can discharge them frequently and get new ones on board of the ship. If you have long voyages, it becomes a challenge. Yeah, just quickly, this is the plan. What we are doing now, we will be installing the fixed piping and the fixed installations on the ship in the first quarter of next year, and then expect Q2 to start with the actual carbon capture, and Q3 next year. If you invite me again, I'll talk to you about if it worked or not.
Most likely not.
Well, okay, then I have to come into Athens then. We did apply for Eurostar funding. I think there were the discussion on the research funding. There is funding available for this, and I think that anybody who has ideas should try this. I hope that we will get the funding. I think it looks good. Besides ourselves and Seabound, we also have Northam and the CMMI and the consortium as well, supporting the whole the pilot phase. So the final one, future. I have to admit, I don't think carbon capture is the silver bullet. It's one of many potential or pieces to the puzzle. One of many solutions. I'm sure that some wind is one. The fuels, low carbon fuels are some. But there are also trials on bigger ships. There are other systems which don't require as much weight in terms of like the pebbles that we are using. But you will always have to carry the CO2 with you until you discharge it. So this is the challenge, hence that means really it is for ships that either are on short voyages or not so much relying on carrying the deadweight capacity. Container ships, for example, where you have smaller or feeder ships, or even bigger container ships where you don't load to the full deadweight. This is a possibility for carbon capture to be used. Finally, I was saying that when we discharge the CO2, it could be used again. And this is the end game. The idea is that the containers will be given ashore. The CO2 will be extracted again through heating, and this CO2 will then be used to produce blue methanol. We are now working on a new building cement carrier for the same client, which will be running on methanol. And if this comes through and this works out, we will be carbon capturing. We will capture the carbon, give it ashore, produce blue methanol, put it back on the ship, use it again, capture the carbon, and so it becomes more or less a circular movement. Sounds fantastic, or too good to be true, huh? Well, it is possible, but of course there are energy losses here, so it's not like it's the silver bullet, as I said. But you're getting a carbon negative propulsion, and this is something that, at least for this ship and for the others that will follow in this with the same system, will help to decarbonize the industry. Thank you very much.